Sorry about that, guys. Good morning. Okay, good morning, everybody. Eva and Cindy. So please open up the slideshow for this morning. We will be getting started in about 1 or 2 minutes for everybody to come back in. Sorry, guys. Good morning, guys.
Really super class.
Yeah. Slides, perfect.
Good job, you guys. All your presentations work out today.
Have a great day, Mr. Walling. Thank you. Janessa is here. Okay, so guys, let's open up our slideshow for today. We will be getting started in about 20 seconds while I get myself, let me just finish doing attendance here. Ian, Adam, and Abby Rasta. Perfect. Okay, so we are opening up our slideshow for today. We're just missing one friend. Wait, is Kyle here? All right, mark that Kyle instead of Janessa. So Janessa is our only friend that is not here this morning. Very cool, very, very, very cool. Let's get started with today's work. Okay, so, let's take a look at our slides for today. So our warm up, actually, I don't know if we have warm up yet. Let me share my screen. And here we go. I'm going to pin myself. I'm going to make it 1, and I'm going to go like this. Let me just pull my chat up over here. Let me grab my chat and let's get started. So for today, we are looking at these slides right here. Let me just get back to slide number 1. So we are building off of what we've been doing a lot with this unit. This unit and the unit before really go hand in hand. And we really go hand in hand, and we're building off of those ideas that we talked about last unit. Last unit, we talked about this concept of no solutions, one solution, and infinitely many solutions. We talked about what those look like in slope-intercept equations, right? So we talked about no solutions having the same variable and the same y-intercept. There's infinitely many solutions. We talked about no solutions having the same slope or variable and different y-intercepts. They're never going to cross. They're parallel to one another. We talked about one solution having different slopes. It's the most important piece, is that they have different slopes. So we're going to take that idea of one solution, no solutions, or infinitely many solutions, and we're going to now apply it to standard form equations. So some of this stuff today should be pretty easy because it's a review of what we did last unit. Some of it should be new in the way that now we're going to be applying it specifically to standard form equations. Standard form equations, meaning we have both our x and our y variable on one side, and it's equal to some sort of constant. So if we have, for example, 2x plus 1y is equal to 20. That's a standard form equation. Our x and our y are on the same side. Okay. We can easily convert that over to slope-intercept, but we're going to be looking at and making distinctions based off the standard form today. Okay. Okay. Wonderful, wonderful. We have a learning target for today. It's very wordy. I'm going to break it down into something simple. So I'm going to read it first, and then I'm going to break it down. So number 1, I can for today is I can tell how many solutions a system has by graphing the equation or by analyzing the parts of the equations and considering how they affect the features on a graph. So the features, the parts that we're going to be looking at, we're going to be looking at our constants. Actually, okay, and because we're talking about standard form equations, I'm going to shift that idea of looking at slopes and variables to coefficients. Okay, so we're going to use this idea of looking at the coefficient. And the coefficient is a more specific, you know how when I say variable, I'm talking about like the letter that's, the number that's attached to the x. So because we're talking about standard form equations now, and we're going to have sort of two different variables, we're going to look at it and we're going to classify it as this idea of a coefficient. So a coefficient is the number that's attached to one of your variables. So if you were to look at this equation, for example, 2x plus 7y equals 20, my coefficients would be 2 and 7, those numbers that are attached to both of my variables. Okay, so the coefficient for the x would be 2, the coefficient for y would be 7. Okay, I'm going to be talking about that, and I'm going to be reminding you of that definition as we move forward. Just wanted to sort of introduce that new, more specific term, just because we're talking about these standard form equations. Okay, so let's take a look at what our assignment is going to be for today. So the bulk of today, we are going to be using our time to sort. We're going to look at 9 different systems of equations. We're going to be looking at 9 different systems of equations, and we are going to be determining the number of solutions that they have. So some of them, I'm going to pull up this slide right here. I would not go to the slide if you're at home. Just look at here. So you have
Mr. Lozier, please call extension 3214. Mr. Lozier, 3214.
So you're going to be clicking on this link to where it's going to have these equations for you, but I want to look at them first. So some of these equations, the first row are all going to, or like the first, I would say like the first 2 at least, are in y equals form. So those ones are going to be easy to distinguish. How many solutions are they going to have? Then they get a little bit more challenging. I want you to you're going to take 15 working minutes in class today to look at these 9. And you are going to determine how many solutions they have. If you need assistance, on the next few slides, we have this link to Desmos. You can do one of 2 things when you're looking at these. If you're looking at a standard form equation here, like for example, if you're looking at card 7, for example, card 7 has a 4x minus 16y equals 16. You have 2 options to figure out and determine this. You can convert it to a y equals equation, or you can use a graphing tool to graph them and use what you know about different solutions, what they look like graphically, to decide how many solutions it's going to
Mr.
have.
Lozier, please report to Food Lab A. Mr. Lozier, please report to Wellness Food Lab A.
Wonderful. So, in summation, 15 minutes are going to be given to you to look at this Elastic assignment on 3 and classify how many solutions each one of these equations is going to have. Once again, a lot of them are already in y equals form. You can either determine the number of solutions by graphing or converting the standard forms into y equals. You have 2 options. It is up to you. If you need a notebook, if you're in school, let me know. You might need a notebook if you are at home, if you need to do some of this work out. Okay? So you're taking 15 working minutes right now. Holy crow. Mr. Main. Yep. Yeah. She was marked absent for Friday. That's what it was. Because I didn't give attendance until this morning. So, well, I mean, I think that's kind of funny because, yes, but also, has she ever Listen. Okay, so yay. Yay. I'm excited. No, that's okay. No, it was because I forgot I forgot to do it. Friday, yep. Wonderful. Maybe you can just say like if you have questions, you can email me too. Like yeah. Yeah, no, that's fine. Yep. Bye-bye. Okay. Here we go. I'm gonna go in. Let's see how you guys are feeling. Question. Yeah? No. Okay, so do you understand what you're doing, Kyle? Perfect. Round of 1313. Oh wow. Lucky number. Okay, I'm gonna go to Edge Elastic. Boom. This one. Okay, Connor is done. Nice job, Connor. You can take a look at slides number 5, 6, and 7. If you finish early, you can take a look at 5, 6, and 7 and start to graph one of the systems that has one solution, one that has no solutions, one that has infinitely many, and insert those screenshots on those slides. Boom. Nice. So Kyle Kelly, please go back and take a look at those ones that you got incorrect, please. Matt, same for you. Make sure you go back and check those ones that you got incorrect. You guys have another attempt, right? Let me see how many attempts you guys have. Okay, yeah, so you have 3 attempts. So if you did not do too hot, go back and take a second look. Take your time though. We still have 10 minutes. Nice job. And those ones that you skipped, dude, you gotta do them all. So. Perfect. Tyler is in there working. Nassim, if you have questions, Abby Wasta, let me know if you have any questions. Peyton, nice job. Ooh, Peyton is moving. Ava, let me know if you have any questions, okay? It seems like we haven't gotten any of them marked yet. That is okay. Just wonderful. Awesome job, John. Make sure you get all 9 of those done.
Mrs. Kulak, please call extension 3223.
You don't have to stop with for X or Y. You can either, I will just convert all of them to like Y equals, just so we can see here. And then we're gonna talk about what it looks like in standard form, so that you don't even have to do that work. Next. Pretty cool. So it says solve for X. You don't have to solve for X or anything. You're just deciding how many solutions each one of these will have. I would check them using graphing. The link for the graphing is on the next slide, 5. John, nice job on number 2. That one looks great. Kyle Kelly, are you back in taking another shot at it, please? Okay, Naseem, what you got correct? Let's see. Oh, you got 100, Naseem. Nice job. Oh, no problem, Kyle Kelly. Nice job, Max. Question.
That's where I can see where I got.
You got 100. So once you finish, I will let you know how you did. Gabe, nice job, 100%. Connor, nice job, 100%. We're actually going to go through the answers as well up here too. So. Wonderful, wonderful. We're taking 8 more minutes, guys. You're doing great. 1 second, Gwen. You got 5 out of 7 or 5 out of 9. So let me see if I can send this back to you. So once you submit it, Gwen, it should let you go back and check your answers. I'll put the ones you got incorrect in the chat, Gwen. Oh, goodness. There you go, Gwen. Nice job, John. The first 2 are good. That last one, maybe take another look at. Nice job, Max. Nice job, Ian. Number 3, Ian. Just take another look at 3. Adam, nice job. The only one you're looking at is number 5. Cam, nice job. Perfect. Let me look, Peyton. 100% Peyton. Woo, woo, woo. Nice job. So you can start to graph on slide 5, 6, and 7. If you finish, you can take a look at 5, 6, and 7. Kyle Kelly, nice job. Nice job, Cindy. Sadie, number 2 and number 5 look good, Sadie. Nice job, John. 1, 3, and 9 are good. Ava, nice job on number 1. Nice job, Pete. So Pete, you got 100. Tyler, nice on number 1. Abby Wasta, very good. Connor, Gabe, if you want to hit submit on those, that would be pretty cool. Or no, maybe not. I think you're good just the way you are, actually. Nice job, Junior. Oh, Junior, nice job on that. You got 100%. You don't need to do it again. Perfect. Nice job, Junior. Sadie, I would take another attempt. Take a look at the ones you got incorrect. Let me see which ones you got incorrect. Attempt 1. So, oh, no, you're good. You're good, Gabe. It's submitted. Yes, you could do number 8, Peyton. Okay, Sadie, here you go. For your second attempt, take another look. We're gonna go through these too, so don't stress out. Anybody. We're gonna go to card view. Junior, nice job. Nice job, Kyle. Nice job, Max. Nice job, Adam. Cameron, very good. You're making some really good progress on that. And you just looking back at 8 and 6. I don't think I got answered. 6 is incorrect and 8 I didn't get an answer for. Nice job, Ava Z. Take a look. Go ahead and start right at number 2. Perfect. Nice job, Junior. We're taking 3 more working minutes. You can start to take a look at and think about slide number 8 as well. Just looking at a system. Nice job, Adam. Nice job, Ian. Nice job, Gwen. Abby, nice job. I would say, Abby, if you wanted to look back at one more, I would say maybe 8, but you're good. Everything's good. Just number 8. Nice job, Ava. Keep working, my friend. You're doing fantastic. Nice job, Junior. I'm gonna grab the door. Wonderful, wonderful. We're taking another minute 42. You're doing fantastic, everybody. Keep up the awesome work. Okay, nice job, John. Making some progress. Keep going. Nice job, Peyton. And I'm going to mark you as completed. Because you've finished. I'm gonna nice job, Cindy, Gabe, Connor. Fantastic. Another 42, and we're gonna get started. Nice job, Gwen. Let me see. Fantastic job. We got 2 incorrect, but we're gonna go through them together. Okay, nice job. 2 attempts is good. Awesome job, Ava Z. You're making progress. I love it, girl. Good girl. Fantastic. Let's come back together and let's take a look. Fantastic. Okay, so we have these 9 cards here. Okay, we had to, I'm going to hit present just so it looks a little bit better. See it a little bit clearer, a little bit bigger. What did we think about card number 1? What did we notice? Adam, what did you notice? You had your hand up. What did you notice? One solution. Okay, so he said one solution. Okay, one solution. And why did we say one solution? Max.
It has the same coefficients. I mean, it has different it has different coefficients and different variables.
Very good.
Not variables,
Very good. Yes, yes, yes. It has different coefficients, those numbers that are attached to our x, right? And in this case, if we want to be more specific, we can say slope. If you say coefficients, that's still 100% correct. That means the same thing in this case as the slopes. Different slopes mean we only have one solution. Good. Nice job on that one. Perfect, perfect. Let's take a look at number 2. What do we notice about card number 2? Did we have to do any work to it? No? Ian saying no. And why did you say no on that one? Exactly. We already have it written in slope form. Very good. And anybody at home, let me know. What do we think? What do we think about this one? How many solutions is 2 going to have? One is saying none. No solutions. Why do we think no solutions for this one? Aguasta. Very good. Same slope or coefficient. Very good. And they had different constants. Very good. Because when we have the same slope and different constants, that means our 2 lines, when we graph them, are going to be parallel. I don't know if the direction on that is right. It's not. It's going to be this way. But they're going to be parallel. They're never going to touch. Awesome job. Number 2 is no solutions. Very good. Jason is saying, Junior is saying, same slope, different y-intercept. Very good. Gabe is giving us a solution for number 3. Gabe said that he thought 3 was going to have infinitely many solutions. Actually, let me erase this so I can do some work underneath it. Infinitely many solutions. And what are we going to have to do to this guy first? Go ahead.
You're going to have to get the 2. You're going to have to get the 2 equations to be like the same.
Okay. And what happens when we do that? How do we have to get them to be the same?
You can either multiply the top one by 3 or divide the bottom one by 3.
Okay. So we could multiply the top one by 3 or divide the bottom one by 3. Okay, good. So I would say I feel better just because I don't want to multiply fractions. I hate multiplying fractions. Terrible. I would say divide the bottom one by 3, and we divide each what by 3? Not each side. We want to be more specific when we're talking about division here. Ian? Very good. We would have each term divided by 3. Very good. And you don't want to get confused. You don't want to be like, oh, hey, that's weird. Because it's our constant and then our x, because it's swapped in the other one. So when we divide by 3, we're left with the equation y equals -9 divided by 3 is -3. And -x divided by 3 is very good, -1/3 x. And you could have written it, you could have also like done like the x over the 3, like if you had written it like x over 3, -x over 3, that means the same. Good. So we converted it to this equation here. And then when we compare them, Gabe said they were exactly the same. So this one has infinitely many solutions. Does everyone see how we did that? Nice job on that one. Good, good, good. Now let's take a look at card number 4. What did we think about card number 4? What did we explain? Aguasta. One solution, and one solution would work. One solution, because we can either convert, like we could either in the second equation move our x over and then compare, or we can take the first one and subtract 3x to get them both into y equals form. Both ways could work. What way did you do? What did you do to compare them? Good. So she converted it to the y equals. Very good. So we could have said 3x plus y is equal to -10. And then to get it into the y equals form, we would, Oh goodness, Mr. Man, you got this. Minus 3x minus 3x. This first equation can be rewritten as y equals negative 10 minus 3x. Okay. And then we would have had to convert the second equation to be a single y by dividing by 3, divide by 3, divide by 3. It would be y is equal to negative 1/3 x minus 10 thirds. I keep it as 10 thirds because thirds is like 3, 3, 3, 3, 3, 3, 3, forever and ever and ever. So if we compare these two equations, what do we notice? And very good. Very different slopes is the most important piece. When you look at two equations and they have different slopes, automatically you don't even need to look at the constants. You say this is only going to have one solution. Okay, one solution for number 5. You could have, like I said, converted, you could have done it in one step and converted the second equation to have the x and the y on the same side, and then compared your coefficients that way. Both ways work. Okay, wonderful. Let's take a look at card number 5. Card number 5, what did we have to do to card number 5? Or what did you do to get it ready to compare? Because I'm looking at it and they're both in different forms. So what did you do? So you said make it a y equals. Okay, so for the second equation, to get it into the y equals, we'd have to subtract 60 from each side. Okay, we'd be 5x minus 60 is equal to 20y. And then get that y by itself by dividing by 20, divide by 20, divide by 20. And then I have to convert this top one as well. Another way that we could have gone about this is we could have converted them both to a single y is equal to, good. I'm not going to go over that because we've done that before. Abby Wasta. Okay, good, good. Yes, 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 yes. Very good. 4y is equal to negative 12, right? So we could have added 4y to each side. Been left with x is equal to negative 12 minus 4y, right? Because if we get them both into the same form and compare your coefficients and constants, we can make those distinctions, right? Because if we look at card number 5 and we rewrite this first one to get the x by itself by adding 4y to each side, now they're both in the form of what x is equal to, and we can make a comparison, right? So if I think about this though, I have a 5x and I have a regular, just a 1x. Ian, what would I do next here? We could use elimination, yes. But how could I get them so that they're both in a single x is equal to? What would I have to do here, Max?
Multiply by 5.
Multiply the bottom one by 5. Good. You could multiply the bottom one by 5 or divide the top one by 5. Same thing. Good. We would be left with a 5x is equal to negative 12 times 5 is negative 60. And then negative 4 times 5 is how much? Oh, you're right. Good catch there, Abby Wasta. Yes, plus 20y. Very good. Nice job there, Gabe, on that one. Good catch on that. Wonderful. So when I compare them, what do we notice? For card number 5, they have the same, or in this case, because it's not in y equals form, we could say same coefficients. We have a 5x, a 20y, a 5x, a 20y, but we have different constants. So this one is going to have no solutions. So when you are asked to to classify equations by the number of solutions that they have, they need to be in the same form. So it can be any form. It could be, you can convert them both to standard form and make your comparisons. You can convert them both to y equals form and make your comparisons. You can convert them to x equals. You have to just have them in the same form in order to make that decision. Does that make sense, you guys? So a lot of, like, this one right here took 2 steps. This one right here took 2 steps as well. These are going to take multiple steps to get them to be in the same form, but that's where the trick lies, is that you can choose what form you want to convert it to. Like, I would say, like, some of these I would convert to y equals, some of these I would convert to standard. It's all based on looking at it, being a flexible math detective. Okay? Nice job, nice job, nice job. Very good. Let's take a look at 6, 7, 8, and 9. I'm not going to go through those ones right now because there is a second piece of this that I want to go through that I think is a little bit more important. Number 6 was one solution because when we converted them, we had the same, we had the x and the x, and then when we compared our y's, they were different coefficients. So we would say because we have different coefficients here on our y values, it's going to be a one solution. Okay, so for one solution, both coefficients don't both need to be different. One of them needs to be different. Okay, so I'm going to say that one more time. For one solution, the coefficients, both of them do not need to be different. As long as one of them is different, and if like the other one's the same, then you know for a fact it's only going to have one solution. 7 has infinitely many because when you manipulate this, and you can convert it to one or two, we can convert it one or two ways. You can add 16y, okay, and then divide all of the terms by 4, okay, and then the two equations would be equivalent to one another, okay. So for this one, I would, if that was me, I would convert it to x is equal to, by subtracting 16y on each side, or adding 16y, sorry, and then dividing all of the terms by 4. You could have multiplied all the terms on the first one by 4 as well. Question, Ian, go ahead.
Divide by 4, do you divide, like, so say it's negative 16 plus 16, why would you also divide the negative 16?
Because the 16x and the negative 16 are two different parts, right? Because one of them have an x and one of them doesn't have an x. So you need to divide each of the terms, each of the parts by 4. Because that's how you maintain equity, is if you do a move to all of the terms, right? Does that make sense? Does that make more sense, Ian? Okay, good. Good. Number 8 is going to have infinitely many solutions because when you, so this is, oh gosh, I would convert this guy to y equals form. Number 5, I would convert to y equals by subtracting 1/5 from each side and then dividing the second equation, all of the terms by 5. That's what I would do. Okay. Last one, and then when we do that, they're going to be equal to one another. Okay. Last one is going to have one solution because when you look at it, same or different coefficients here. We have a 2x and we have a 4x and we have a single y. Okay, good. Nice job on that, guys. Okay, let's take a look at the next piece of this. Okay, so what we had to do is we had to graph these 3 equations using Desmos. I'm going to give you 2 minutes right now to pick any of the sets, right? And you're going to decide, you're going to graph all 3 of these on Desmos. So you're going to pick one that has one solution, one that has no solutions, one that has infinitely many, and you're going to insert those pictures onto the slide. I'm going to put up here the answer key so that you can go back and easily type them into Desmos. So click on that link on slide number 5 to open up Desmos. Find 3 of these, plug them in, and get the graphs and insert them in. Okay, you're taking 2 minutes right now to do that. Okay, very good. I'm gonna leave this guy up here. Close this guy out. You don't need pictures on slide number 8. We're gonna talk about that. And I'm not gonna go through these. I'm gonna ask you what they look like. Because this is something that we did last unit, so this one should be easy peasy lemon squeeze. Wonderful, wonderful. Another minute and 14. If you don't get this done, that's okay. If you don't remember how to screenshot, let me know. Oh, yes, yes, sorry, Gwen. There we go. It also should be on your slide number 4 in your slideshow as well. Nice job, ladies and gentlemen. You got another about 23. Wonderful, wonderful. Let's move forward. Okay. Let's take a look. So we're going to talk about some of the things that we notice. I'm not going to go through and graph these. I'm not going to graph 3 of them because this is something that we've been doing this unit and last unit. What do we notice about the ones that have one solution? In general, what do we notice about the graph? Go ahead.
They only have one point where they intersect.
Very good. They only have one point of intersection. So it could look like this one point of intersection. It could look like really not steep. It could be 2 really steep lines. We know that one solution only has one intersection point. You don't need to write this down. You don't need to write this down, okay? Very good, nice job. We know that all that have one solution only have one intersection point. Now, someone at home, tell me, what does a graph that has no solutions in general look like? What do we think? Awesome job, Peyton said that the 2 lines, the 2 equation lines are parallel. For my friends in the back, what does parallel mean? What does it translate to? Layman's terms, Abby Wasta. Exactly, 2 lines that will never touch. Never, ever, ever gonna touch. Very good, nice job, Peyton, Gabe, and Abby Wasta. Yes, fantastic. Now, last piece. What does an infinitely many solutions mean or look like when we're talking about a graph? Graphically, what's it mean? Cam?
There's only, like, the lines are just one straight line. There's no, like, 2.
There-
They're just on each other.
Yes, they fall on top of each other. Okay, yeah, very, very, very good. If you have infinitely many solutions on a graph, it looks like one line. So when you're given a system and you have the opportunity to graph it in order to determine how many solutions it's gonna have, if you graph it and you're like, there's only one line there, I must have done something wrong. No, you didn't, probably. 99% chance you got it right. If there's only one line on your graph, that means they are infinitely many solutions because they fall on top of each other. They have the same coefficients when we look at the graphs. Good, nice job. Wonderful, wonderful, wonderful. Now, wrap up for the day. Okay, I know there's still a lot more slides, but this is where this and then the next two are where we're really hitting it home. Okay, these are the main takeaways from today. So, actually, we're going to do these a little bit out of order. I want to look at 9 and 10 first, and then we're going to go back and do 8. Okay, because 9 and 10 are where I'm really hitting something home, and then 8 is where we can sort of discuss. Okay, so when we have, this is a review from last week, when we have slope-intercept form equations and we graph them, one solution means that they're going to fall on top of one another. They have the same line. Or no, sorry, Mr. Ray was confused for a second. I was looking at the wrong one. One solution means that they have different equation lines, different slopes. No solutions, remember, had the same slope, equal slopes, different y-intercepts or coefficients. Last piece was we had infinitely many has equal slopes, same y-intercepts. So the slopes are the same, the y-intercepts are the same, constant. When we looked at equations, we said that equations had different slopes for one solution. Okay, no solutions had the same slope, but different y-intercepts. Infinitely many had the same slope, the same y-intercept. That is a refresher. Now, let's take a look at what these would look like for standard form equations. Okay, so when you're given a set of equations in standard form, and we need to decide without even graphing them, are they going to have the same solution, no solutions, or one solution? Let's take a look at how we're going to do that. So let's match some of these graphs first. So one solution graphically, it's going to look the same. Which one of these, 1, 2, or 3, represents one solution? 1, 2, or 3?
3.
Oh, 3. Yes, nice job. Very good, very good. One solution has 2 different equation lines, different slopes, okay? Then no solutions, which one of these that are left? The first one or the second one? Second one, good. Last one is infinitely many because we said the graphs overlap each other. Whether you graph equations in standard form or y== form, they're still going to look the same. Each graph is still going to look the same. If you have 2 the ones that fall over each other, and you're graphing them in standard form, you're still going to say infinitely many. Same thing for no, same thing for 1. They're still going to look the same graphically when you graph them. The part that's different are these descriptions right here. So let me pull these descriptions up so that we can see them a little bit better. Okay. So if we look at these descriptions here, let me make this a little bit nicer because I can't really see this. Okay, let's look at these descriptions here. Okay, it says when we're looking at these equations, the first one says the x and the y variables have the same coefficient and the same constant. So the x and the y have the same coefficient, and that constant on the other side of the equal sign is the same. What do we know about those, the solution for that system? And which one? Infinitely many. Very good. This guy right here is going to have infinitely many solutions because it has the x and the y variables have the same coefficient and the same constant. When we look at this equation here, if you look at this system here, they don't look like they have the same one here, but if I were to multiply this second equation, this first equation here by 2, all of the terms, my x's would be the same, my x coefficient, my y coefficient, and my constant would all be the same. So this guy, I would match up with infinitely many solutions. Very good there. Nice job, Ian. Now we're left with these other 2 here. Okay. They say, number 1 says the x and y variable have different coefficients. What do we know about the solution that if we're in standard form, the X and the Y have different coefficients when you're looking one to the other? What do we think? It's gonna have one solution, very good, because if we look at this example here, let me just wait for this to go away, sorry guys. If you look at this equation, this system here, we have a 4x plus 5y equals 20, and we have a 7x minus 6y is gonna be equal to 20. So because they're both equal to 20, we know right away that's gonna be a no-go, because our coefficients are different. But also, if we look at and we try to manipulate these, there's no way that we can manipulate these so that the x's and the y's have the same coefficient, top to bottom, okay? And then, so this, obviously, this last one would go here, where no solutions would look like the x and the y variables have the same coefficient and a different constant. So on the left-hand side here, or wherever your variables are, your x's have the same, your y's have the same. If I were to multiply the top one by 2, we would have the x and the y be the same, but our coefficients would be, our constants would be different. I might have written this one a little bit wonky, and I actually made this one, I'm going to make it a 17 because, or I'm going to go 27. I'm going to go 15 because those were the same when you multiply by 2. I messed up. But yes. Good. So now we're talking in general. Okay. If you just have a system of equations, and I'm asking you without graphing, how many solutions is it going to have? And they're both in standard form. What is one solution going to look like? If you're looking at a standard form system, and I'm telling you, you cannot solve it by graphing, how are you going to figure out how many solutions it has? Abby Wasta. Very good. Coefficients. And we can say different constants. But that's not always, like you could have, so I could give you an equation, like for example, 5x plus 7y equals 30, and 2x plus 10y equals 30. We'd have the same constants, but because the variables are, the coefficients are different, is really the most important piece. So the most important piece is that if you look at the standard form equations and they have coefficients that are different, automatically you can say no, one solution. Okay. So yes, different coefficients sometimes, but not always. So don't get hung up on that coefficients and variables are, and constants are different. Just the variables or the coefficients need to be different. Good job, Peyton. Nice job. Nassim, yes, sorry, buddy. Now, how can we tell if the system has no solutions? If we're looking at a system in standard form, how do we know if it has no solutions? Max.
There's the same coefficient with different constants.
Very good. Same coefficients and different constants. I'm telling you right now, I'm probably never going to spell coefficients. There's 2 X, I do know that though. So same coefficients, different constants. I'm not taking points off on spelling if I can sort of tell what it is, right? So like if you have like a COF, like you're good. Last one, how can we tell if the system has infinitely many solutions in standard form? Aiden, help me out. Go ahead. So, yes, I agree, but we're talking about standard form, and we said we're not going to use that word slope anymore. We're going to call them coefficients. So the coefficients and the constants are the same. And we want to use that word coefficients because when we're looking at a standard form equation, we can calculate what the slope is, but slope is like a slope-intercept form type deal. It's not like you don't look at a standard form and say that number right there is the slope. You have to do some work to calculate what that slope is. So we're going to call them coefficients. Good. Awesome, awesome, awesome. Okay. So, ladies and gentlemen, you have on your slideshow for you have 11, 12, and 13, and 14. You don't have to do anything with those. You're not doing anything with 12, 13, or 14, or 11. You're not doing anything with the last, up until the second to last one. Homework for this evening. Yours looks a little bit different because I made my copy a little bit before I made a change to yours. So yours actually has links. Tonight, you have a quiz review. We're going through the quiz review tomorrow because we have a quiz on Thursday. So it's a good idea for you to get started on that quiz review tonight because we are going through all those answers tomorrow, okay? The format is going to be almost identical to the quiz that we're going to be taking. There are a few more questions on the quiz review than there are on the actual quiz. So that's pretty cool. And you want to keep in mind midterm review 1 through 19 tentatively is due on Friday. So I'm not going to go in on Friday and say every class only has 1 through 18 done. She only gets 18 points. I'm saying for you, so that you have it done for when we're going to go through these things, you want to try to have 1 through 19 done by Friday. If you only get through like 1 through 10, that's okay. Because I'm probably not going to be getting through all the way 19 for on Friday. I'm going to be strategic in the ones that I'm picking. Okay. Questions for me? You don't have to do anything with the rest of the slides here. You need to do the quiz review for homework this evening. Okay. If you have Spanish, you can jump out. If you have Spanish, you can jump out. If you have Spanish, you can head out there. I want everybody that's not taking Spanish to stay in though, because we're going to do something in Alex today. Awesome job. Have a great day. I will see you guys later. Awesome, awesome, awesome. I'm so glad you got guys. Wonderful, wonderful, wonderful. Let me give me 1 second. Let me just stop my share. Okay. Okay. Hello, Sadie, Junior, Nassim, Kyle, Connor, John, Gwen, Janessa, and Tyler. So what we're doing for ourselves right now is we are going into Alex. Everybody here is going into Alex. Okay. Everybody should have their login information because we did it this morning. If you don't have it, I need you to let me know because I'm going to be checking to make sure that everybody is signed in. So if we go into Alex, there might be something assigned for you. Let me show you what that might look like. Give me 1 second. Let me see who has it assigned still. Okay, so if you go into Alex, there is an assignment on the left-hand side of your screen that is called Scheduled Knowledge Check Winter. You might have to work on that. Hello. Who is it? Jonah P. I can send him an email with that in about 30 seconds. Wonderful. Yep. Okay. So let's see who has not finished. So Tyler needs to finish their knowledge check. Janessa, I'm going to send you your information and you're going to get logged into Alex, and everybody else is working on their path. Okay. Everyone else is working on their path for Alex today. I'm going to get Tyler, Janessa. Give me 1 second, Janessa. I need class roster.